Hello, my name is Yuli Lupera, and today I'll be teaching you a little bit about ciprofloxacin. Ciprofloxacin is a broad-spectrum antibiotic. Much like penicillin and amoxicillin, it is a fluoroquinoline, which means it interferes with the DNA replication of bacteria. That's how it gets it to stop replicating, and it often combines with other compounds to treat specific conditions, such as we see here. It combines with hydrochloride to be used as an eye solution for bacteria in the eye. It can also be used for bacteria in the ear, and it can be taken on its own. On its own, it typically treats respiratory and urinary infections. Some common information about ciprofloxacin: the IUPAC name is 1-cyclopropyl 6-fluoryl 1,4-dihydro 4-oxo 7,1-piperazonyl 3-quinoline carboxylic acid. It has a molecular formula of C17H18FN3O3 and a molecular weight of 331.34 grams per mole. It has a melting point range of 255 to 257 degrees Celsius, and it's a carcinogenic and an irritant on its own. So on the right hand side here we have the Lewis dot structure, where all lone pairs and bonds are displayed, and here on the left hand side we have the more simplified skeletal stick structure. Ciprofloxacin has various functional groups, such as this carboxylic acid right here. It also has a ketone, a benzene ring, and various amine groups, such as a secondary amine connected to 2 carbons and these 2 tertiary amines connected to 3 carbons. It also has various bond angles, as observed here in this 6 atom ring. All the angles are 109 degrees, 109.5. Here on this nitrogen, between the hydrogen and its bonds with the carbon, it's 109.5, as well observed in this nitrogen over here and the nitrogen over here. The cyclopropane has bond angles of 60 degrees. And then in the benzene rings and in the double bonded atoms, we observe 120 degrees, such as here in the benzene ring. Here in this carbon oxygen bond, in this other pi bond over here, and in this bond over here. We observe that's 109.5 here in the oxygen because it is bonded to a carbon, a hydrogen, and it has 2 lone pairs. Ciprofloxacin has various polar bonds, such as the ones observed in the amines groups, where the nitrogen is partially negative and the carbon or hydrogen is partially positive. We can also observe another polar bond here between the carbon and the fluorine, where the fluorine is partially negative and the carbon is partially positive. Here at the ketone, we can observe that the carbon is partially positive and the oxygen is partially negative. Here at the carboxylic acid, we can observe the same thing, with the carbon being partially positive and the oxygen being partially negative. Here with this oxygen, we can observe that both dipole moments are pointing towards the partially negative oxygen, so both the carbon and the hydrogen are partially positive. These polar bonds from ciprofloxacin allow for it to be soluble with polar compounds, but it also has various nonpolar hydrocarbon bonds which allow it to interact with nonpolar solvents. This makes ciprofloxacin a moderately polar solvent, such as ethyl acetate and acetone, meaning that it won't be as soluble at room temperature in highly polar solvents such as water, making water a good crystallization solvent, since at room temperature it won't be as soluble, but at higher temperatures it will. Shapes in ciprofloxacin. So ciprofloxacin, we can observe it has trigonal pyramidal right here at the amine groups due to the lone pair. We can observe here tetrahedral shapes at the carbons because they are at the sp3 carbons, and it's trigonoplanar at the sp2 carbons because of the pi bond. We can observe more trigonoplanar at the sp2 carbons. Here at this oxygen, this is bent shaped because it has two lone pairs and it's connected to a carbon and a hydrogen. And we observe more tetrahedral at these sp3 carbons in the cyclopropane. Hybridization and pi bonds. So ciprofloxacin has various pi bonds, and such as in the benzene ring, the ketone, and the carboxylic acid, the oxygen here in the carboxylic acid. And this is where it's sp2 hybridized because of the pi bond, and then everywhere else on the atom it is sp3 hybridized, such as in the carbons, the nitrogens here in the amine groups, the carbons here in the cyclopropane, the oxygen here that's single bonded from the carboxylic acid. Resonance. Ciprofloxacin does not have primary resonance structures, but it does have secondary resonance structures, such as the ones observed on the screen. When we have a movement of electrons from this amine group, the lone pair on the amine group to create a pi bond all the way down to this ketone, we end up having a positively charged nitrogen and a negatively charged oxygen where the ketone needs to be. We can also have movement of electrons here in this carboxylic acid. The electrons from the oxygen can move to create pi bonds, and the electrons from the pi bond can move to this oxygen, leaving us with a positively charged oxygen and a negatively charged oxygen. Likewise, with the one on top, we can have movement of electrons from this lone pair of the nitrogen all the way, but instead of the ketone, to this pi bond in the carboxylic acid, and we'll end up with a partially charged nitrogen and a negatively charged oxygen. It's good to mention that the top structure and the bottom structure are more stable than the middle structure because the nitrogen can hold the positive charge better and will be more stable with the positive charge than the oxygen. So ciprofloxacin has various hydrogen acceptors and donors, such as the nitrogens here in the amines, amine groups. This nitrogen here, because it has a hydrogen, it can accept and donate the hydrogen. We have the fluorine right here, which can also accept hydrogens, and the oxygens here from the carboxylic acid and ketone can accept, but this oxygen with the hydrogen can donate this hydrogen. Ciprofloxacin contains a carboxylic acid, as mentioned previously, which contains the most acidic hydrogen. So in the presence of NaOH, the OH will take the hydrogen and we'll have the formation of water and a negatively charged oxygen. This does have resonance, so there is movement of electron and a delocalized negative charge between these two oxygens on what used to be the carboxylic acid. Ciprofloxacin has various basic parts, including the amine groups, with the tertiary amines being the most basic, and in presence of an acid such as HCl, the lone pairs on the amine groups will take that hydrogen and will have a positively charged nitrogen and a negatively charged chlorine. Ciprofloxacin does have 14 different carbon environments, and in this sample carbon 13 NMR spectrum, we observe 13 peaks. So we have the carbon hydrogen, which is anything from 10 to 60. We have the carbon nitrogen bonds from the amines, which is anything from 40 to 70. We have the carbon double bonded carbons from the the alkenes in the benzene ring. And we also have the C double bond O's. This one right here is probably from the carboxylic acid, and the one a little bit higher is from the ketone. Lastly, we have a IR spectrum sample For ciprofloxacin, we have a C double bond C peak from the benzene ring, a C double bond O from the ketone, a COOH peak from the carboxylic acid, some CH peaks here, the sp3 peak, and an sp2 peak from the benzene ring and pi bonds. And that's the conclusion of this little presentation. Thank you for watching.